Hello everyone. Welcome to yet another topic of mathematical expectation. Today we are going to discuss characteristic function. Yesterday we have studied moment generating function, but moment generating function do not exist for many distributions. But this characteristic function exists for all distributions. It is defined as it is denoted as phi x of t, and it is defined as expectation of e raised to I tx, where I is equal to root of minus 1. It exists for all distributions. So we can study the properties of distribution using characteristic function. Next, if x is a discrete random variable, phi x of t is equal to summation over x e raised to I tx p of x. If it's a continuous random variable, phi x of t is equal to integral e raised to I tx f of x dx. Okay. Then how we find moments from this characteristic function? As similar as moment generating function, we can generate moments from this characteristic function using the expansion. The coefficient of it raised to r. The coefficient of it raised to r by r factorial in the expansion of phi x of t is the rth row moment of x. So phi xt is equal to expectation of e raised to I tx. Expanding, we get expectation of e raised to I tx is 1 plus I tx by 1 factorial I tx whole square by 2 factorial plus etc. Rth term is I tx all raised to r by r factorial plus etc. So it is expectation of 1 is 1 plus it into expectation of x by 1 factorial plus third term is it whole square into expectation of x square by 2 factorial plus etc. Rth term is it all raised to r by r factorial into expectation of x raised to r plus etc. So we can see that the coefficient of it by 1 factorial is expectation of x. Coefficient of it whole square by 2 factorial is expectation of x square. Similarly, the coefficient of it raised to r by r factorial is expectation of x raised to r or mu r dash. So we can find the row moments r is equal to 1, 2, 3 etc. like this. Okay. Another method is for finding rth row moment like MGF. It is by differentiating phi x of t d raised to r by dt raised to r of phi x of t at t equal to 0, we get rth row moment. Okay. Next, a problem. Find characteristic function of a random variable. Find characteristic function of a random variable with x with the probability mass function f of x equal to e raised to minus lambda raised to x by x factorial. X is equal to 0, 1, 2, etc. This is Poisson distribution. You will study this distribution in this semester. Then by definition, phi x of t is equal to expectation of e raised to I t x. So summation, it's a discrete distribution, so summation over x is equal to 0 to infinity e raised to I t x, here probability mass function is e raised to minus lambda raised to x by x factorial. Okay, so it is summation over x is equal to 0 to infinity e raised to minus lambda e raised to minus lambda e raised to I t all raised to x divided by x factorial. So e raised to lambda taking outside, we get summation over x is equal to 0 to infinity lambda e raised to I t all raised to x by x factorial. Substituting we get e raised to minus lambda outside, lambda e raised to I t all raised to x by x factorial. So lambda e raised to I t all raised to 0 by 0 factorial plus lambda e raised to I t all raised to 1 by 1 factorial plus lambda e raised to I t all raised to 2 by 2 factorial plus etc. Okay, so e raised to minus lambda e raised to I t by I t all raised to 0 by 0 factorial is 1, and next term is lambda e raised to I t by 1 factorial. Next term is lambda e raised to I t whole square by 2 factorial plus etc. Okay, this is the expansion of e raised to lambda e raised to I t. Okay, so multiplying we get it is e raised to minus lambda plus lambda e raised to I t, okay, which is equal to e raised to lambda into e raised to I t minus 1. So the characteristic function of the given distribution is e raised to lambda into e raised to I t minus 1. Okay. Next, properties of characteristic function. We study the basic properties of characteristic function. First property, phi x of 0 equal to 1. Phi x of 0 equal to 1. For all real t, phi of 0 equal to 1. So phi x of 0 is, by definition, phi x of 0 is equal to expectation of e raised to I into 0 into x, okay, which is equal to expectation of expectation of e raised to 0. E raised to 0 is 1, so expectation of 1 is equal to 1. So for all real t, we have phi of 0 is equal to 1. This is the first property. And second property is for all real t, modulus of phi x of t is less than or equal to 1. Modulus of phi x of t is less than or equal to 1. We suppose let x is a continuous random variable. We are doing this taking x as a continuous random variable. So let x be a continuous random variable. Then modulus phi x of t. By definition, it is modulus integral over x or integral over minus infinity e raised to I t x f of x dx. Okay. We know that it is less than or equal to integral over x e raised to I t x f of x dx. So it is less than or equal to integral over x e raised to modulus of e raised to I t x f of x dx. Since f of x is always it's a probability density function, so it is f of x is always greater than or equal to 0 for all x. So then we e raised to I t x, we know e raised to I t x, modulus of e raised to I t x is plus 2 e raised to I t x is cos t x plus I sin t x. Its modulus value is root of cos square t x plus sin square t x, which is equal to 1. So modulus phi x of t is less than or equal to integral over x. Modulus e raised to I t x is 1 and rest is f of x dx, which is always its maximum is 1. So it implies that it's less than or equal to 1. So if x is a discrete random variable, the sign integral sign is replaced by summation. The proof will be same. Okay. Next, third property. We are studying the basic properties of characteristic function. Another property is phi x of t and phi x of minus t are conjugate functions. Conjugate functions. I hope you know the conjugate function. That is conjugate function means phi x of minus t equal to phi x of t bar. It's a complex function, so phi x of minus t is equal to phi x of t bar. Okay, so proof is phi x of t. We know that phi x of t is expectation of e raised to I t x, which is expectation of cos t x plus I sin t x, and phi x of minus t is expectation of e raised to minus I t x. So expectation of e raised to minus I dx is cos tx minus I sin tx. Okay, so it is the phi x of t bar. The expectation of cos tx minus I sin dx is phi x of t bar. Therefore, phi x of t and phi x of minus t are conjugate functions. Okay. Next property. If the distribution function of a random variable x is symmetrical ഒക്കെ നിങ്ങൾ പഠിച്ചതാണ്. സിമെട്രിക്കൽ ആണെങ്കിൽ എന്തായിരിക്കും എന്നുള്ളത് നിങ്ങൾക്ക് അറിയാം. സിമെട്രിക്കൽ about 0 that is 1 minus f of x equal to f of minus x അങ്ങനെയായിരിക്കും, which implies that f of minus x is equal to f of x അങ്ങനെയായിരിക്കും സിമെട്രിക് ആണെങ്കിൽ ഡിസ്ട്രിബ്യൂഷൻ. then phi x of t is real valued. Phi x of t is real valued and even function of t. Okay, എങ്ങനെയാണ് നമുക്ക് തെളിയിക്കേണ്ടത്? തെളിയിച്ച് നോക്കാം. By definition, we have phi x of t is equal to integral over x e raised to I t x f of x dx. Here I am taking x is a continuous random variable. So here the x is symmetric. So f of x is equal to f of minus x. രണ്ട് എക്സും ആകുമ്പോൾ കൺഫ്യൂഷൻ ആവേണ്ടെന്ന് വെച്ചിട്ട് ഞാൻ അടുത്ത് y ആയിട്ടാണ് എടുക്കുന്നത്. സോ put x is equal to minus y, which is equal to integral over x ഇത് minus infinity to infinity റേഞ്ച് ആണ് എടുത്താൽ മതി. minus infinity to infinity ആണ്, അങ്ങനെ പറയുമ്പോൾ കൺഫ്യൂഷൻ വരില്ല. സോ e raised to minus I t y f of minus y dy. Phi x of t is equal to integral minus infinity to infinity e raised to I t y f of minus y dy, which is equal to but given that f of minus x is equal to f of x, so which is equal to integral minus infinity to infinity e raised to minus I t y f of y dy. Okay, so this is phi x of minus t, which implies that ഇതെന്താണ് മനസ്സിലാവുന്നത്? എന്താ മനസ്സിലാവണേ? phi x of t എന്ന് പറയുന്നത് ഈവൻ ഫംഗ്ഷൻ ആണ്, which implies that phi x of t is an even function of t. So phi x of t equal to phi x of minus t, which is equal to phi x of t bar. Phi x of t equal to phi x of minus t equal to phi x of t bar. So it is a real valued and phi x of t is a real valued and even function of t. നേരത്തെ പ്രോപ്പർട്ടിയും കൂടി ഒരുമിച്ച് ചേർത്താണ് എഴുതുന്നത്. Okay, നെക്സ്റ്റ് നമ്മൾ നേരത്തെ MGFൽ തെളിയിച്ചതുപോലെ തന്നെ let x be a random variable with a characteristic function phi x of t, then the characteristic function of y equal to ax plus b. What will be the characteristic function of y is equal to ax plus b, where a and b are constants? It is e raised to I bt into phi x of at. ഓക്കെ, എങ്ങനെയാണ് ചെയ്യാൻ നോക്കാം. നമുക്ക് നേരത്തെ നമ്മൾ ചെയ്തതാണ്, അതുപോലെ തന്നെ ചെയ്യാം. പ്രൂഫ് ബൈ ഡെഫിനിഷൻ phi ax plus b of t is equal to expectation of e raised to it. x എന്നുള്ളടത്ത് ax plus b which is equal to expectation of e raised to it ax plus it b. Okay, so it is expectation of e raised to it ax into e raised to it b. Taking constant outside, so e raised to itb no ibt no പറയാൻ എളുപ്പത്തിന് e raised to ibt into expectation of e raised to itax or iaxt, which is equal to e raised to ibt into phi x of at. Okay. Okay, these are the main basic properties of characteristic function. Next main property is uniqueness theorem and uniqueness theorem and continuity theorem. But they are the beyond the scope of your syllabus, so these properties are enough. Okay, thank you. Okay, before I wrap up, I state the uniqueness theorem, because it is the important theorem. This is one of the most fundamental theorems in distribution theory. It enables one to identify the form of the distribution of a random variable from its characteristic function. So it states that characteristic function uniquely determines the distribution function of a random variable. That is, corresponding to a given distribution, there is only one characteristic function, and corresponding to a given characteristic function, there is only one distribution. Okay, this is an important theorem in distribution theory. Okay, the proof is is beyond your scope of your syllabus, so statement is enough. Okay, thank you.